Hello everyone, welcome to the channel ABC Chemistry. In this video, I will cover second part of infrared spectroscopy. And this video will help you to understand Hooke's law and the frequency of vibration. Now you must be wondering, what is this Hooke's law? So let us first understand it. Law is scientifically what? An observed phenomenon. So, a person named Hooke long time ago observed elastic objects. So, this law is all about stretching springs and other elastic objects. So, what he did at that time, he took a spring, as you can see right here, and he attached one end of the spring against a wall, and to the other end of the spring, he applied a precisely known force by attaching a weight of a known mass so as to stretch the spring. So, this is here where he attached the weight of known mass. So, from this, he concluded that the stretched spring will try to get back to its original position whenever the force will be removed. Secondly, he concluded that the extension produced in the spring is proportional to the force applied. So, higher the force applied, more will be the extension produced in the spring. And this proportional means that both of them are linearly related to each other. Linearly means if one of them will increase, the other factor will increase too. Let us understand this more in detail about how he made his conclusions. I have shown the same case here which I just talked about before. So here one end of the spring is fixed, as you can see, and to the other end of the spring a weight of known mass is attached in order to apply a force, and the spring is undergoing continuous extension and compression. Case A, when the spring is stretched. Now, in order to stretch the spring, we have to apply the force in the right direction. And because of that, spring will be displaced from its equilibrium position. Now, at that point, if we will remove that applied force, what will happen is that the restoring force, means the force due to spring, will try to bring the spring back to its original position. So, as it is restoring the spring, that's why it's known as restoring force. The point which we have to note here is that the applied force, which is represented by Fa, and the restoring force, which is represented by Fs, they both act in opposite directions to each other. So if the applied force is acting towards right direction, the restoring force will act towards the left direction so that it can restore the spring back to its original position. In case B, when the spring is compressed. Now, in order to compress the spring, we have to apply the force in the left direction, and the spring will be displaced from its equilibrium position in the left direction too. Now, at this point, if we will again remove the applied force, what will happen is that the restoring force, or the force due to spring, will try to bring the spring back to its original position, and this time it will be acting towards right direction. So again, you can see here, if the force we are applying is towards left, the restoring force due to spring is acting towards right. So from this whole phenomenon, what Hooke concluded was that the extension produced in the spring depends upon the force applied. So if we will apply a larger amount of force, more will be the extension noticed in the spring and vice versa. And the second thing which he noticed was that the restoring force always acts in opposite direction to the displacement produced in the spring. So if I talk about any one of the particular case here, suppose I talk about the stretched one, you can see that if restoring force is acting towards left, it means the displacement was taken towards right direction. Let's do it. You can observe the same thing practically either by stretching a rubber band or a spring. So if you have either of them at your home, and if possible, just go and grab one and try to do the way I will instruct you. Step A, when the spring is at rest, and K here represents the strength of the spring. Now in the shown picture, one end of the spring is tied against the wall or something else, and the other end of the spring is held in your hand. Now if you don't have anything to tie your spring with, what you can do, you can hold it in your left hand, but make sure your left hand is still. It doesn't move and it doesn't apply any kind of force on the spring. Moving on to step B, what we will do here, we will try to pull the spring by applying the force in the right direction. So you can notice the same thing happening here in the picture shown with the arrows. Now at this point, if you will remove the force or if we will release the spring from our hand, what will happen? The restoring force due to spring, which is shown with the green arrow, it will try to restore the spring back to its original position. And because of that, we will notice the extension and compression going on in the spring, or we can say that the spring is vibrating. So when you are doing this activity, you will notice two things, that the amount of extension produced in the spring depends upon how much force you are applying. Second thing is that the spring is getting displaced in the direction opposite to the restoring force acting in the spring. The one thing which has to be taken care of is that the force should be applied to a certain limit, and if you will apply beyond that, or if you will try to exceed that limit, your rubber band or your spring can break. So just be mindful about that thing. So according to Hooke's law, the restoring force of an ideal spring is given by the expression Fs is equal to minus K times X, where Fs is representing the restoring force, the force due to spring. So that's why we have this S used here for spring. And the units to measure the restoring force are dynes. K represents the spring or the force constant, and the units of measurement are dynes per centimeter. X represents the displacement shown by the spring, and it is measured in centimeters. This minus sign, which is used here in this expression, this indicates that the restoring force always points in a direction opposite to the displacement shown by the spring. And this type of system behaves like a harmonic oscillator. So whenever we will try to disturb our system from its equilibrium position, the restoring force will be acting in the direction opposite to the displacement produced in the spring. And such systems behave like harmonic oscillators, and they will start producing vibrations in them. Hooke's law states that the frequency of vibration of the spring is related to the mass and the force constant of the spring by the following formula. Let us see this formula. Nu is equal to 1 upon 2 pi root k upon m, where nu represents the frequency of vibration. with what frequency the spring is vibrating or undergoing extension and compression. K represents the force constant or the force due to spring, and it measures the strength of the spring. Larger the value of K, stronger is the bond and higher is the frequency of vibration. So as you can see in this expression, the frequency is proportional or linearly related to this force constant. So if one will increase, the other factor will increase. Second, the mass M is the mass attached to the spring. Smaller the value of M, higher is the frequency of vibration. Because in the expression, the frequency of vibration is inversely proportional to the mass M attached to the spring. So if one of them will increase, the other factor will decrease because they are inversely related to each other. Molecular vibrations and Hooke's law. So the phenomenon which was observed in case of springs, the similar phenomenon was noticed in case of molecules, because we know that the bond between the molecules or two atoms is not rigid, rather it behaves like stiff springs or elastic springs. And as you can see here, that bond is undergoing continuous extension and compression when the atoms in the form of masses are attached to it. So molecular vibrations involves the periodic motion of the atoms of a molecule relative to each other such that their center of mass doesn't change. And during those vibrations, this diatomic molecule, which is vibrating, behaves like an oscillating spring. Due to that, a vibrating bond in the IR spectroscopy can be compared to the physical model of vibrating spring that can be described by Hooke's law. So basically, a comparison has been done between the vibrating spring and the vibrating bond in the IR spectroscopy. So as you know, whenever the bond is made to interact with infrared radiations, and when the wave number of IR radiations will match to the wave number of that bond vibration, it will absorb those radiations and it will start producing molecular vibrations in it. So because of that same scenario, a comparison has been done here. So frequency of vibration of the bond can be calculated using Hooke's law, and here the two atoms are considered as point masses having mass m1 and m2, and the bond between them is represented with the spring of force constant K. The frequency of vibration of the bond is calculated by the shown expression, where nu is equal to 1 upon 2 pi root k upon mu. Nu is representing the frequency of vibration, as I have already told you, but this time we are talking about the vibration of the bond. K is the force constant, which measures the strength of the spring, or I can say here the strength of the bond. And mu represents the reduced mass, which is equal to m1 m2 upon m1 plus m2. And the units are grams per atom. So this expression is almost similar, which was used to measure the frequency of the spring. A slight change is that instead of mass m, we are using reduced mass here. The approximate wave number of an absorption can also be calculated using Hooke's law expression. Nu bar is equal to 1 upon 2 pi c root k upon mu, where nu represents the wave number and it is measured in units of per centimeter. C is representing the velocity of light, which is equal to 3 times 10 the power 10 centimeter per second. K is the force constant and mu is the reduced mass. This expression is almost similar to the expression which was used to measure the frequency of vibration of the bond. So if you will substitute nu bar with nu upon C, you will get the same thing. So wave number of IR absorption is equal to the wave number of stretching vibration. So what is done in IR spectroscopy is that using the above written expression, the wave number of stretching vibration for particular bonds are calculated. And once they are known, we know that the same wave number of IR radiations are required in order to show the absorption. So frequency of vibration depends upon two factors, as we have already discussed. The first one is the force constant K, which measures the strength of the bond. And this time we are discussing this factor with the help of some data. So bonds, we have got three types of bonds here. We have carbon single bond carbon, carbon double bond carbon, and carbon triple bond carbon. And if you will see, the force constant or K is higher for carbon triple bond carbon, because we know triple bond is stronger in comparison to double bond, and double bond is stronger in comparison to single bond. So similarly, the values of K are getting varied. So as the triple bond is stronger, it means the bond energy is higher, and bond energy, force constant, both are higher. It means the frequency of IR absorption will be higher, and that bond is going to vibrate with higher energy. That is why the arrow is shown up. So from here, one thing which we can conclude is that the energy of vibration is proportional to the frequency of absorption, and this frequency of absorption is proportional to the force constant K. So these are linearly related to each other. And if you want, you can add bond energy also. Second factor is the mass of the atoms which are attached to the bond. So here, if you will see, I have taken all the singly bonded molecules. So we have carbon-hydrogen bond, we have carbon-carbon bond, carbon-oxygen bond, carbon-chlorine bond, and carbon-bromine bond. And as I am moving downwards, the mass of the atoms which are attached across this single bond is getting increased. And because of that, their reduced mass will be higher. As we know, the frequency is inversely proportional to the reduced mass, so their frequency of absorption will be lower. Or other way I can say that when we are moving up, the reduced mass is getting decreased and the energy of vibration or the frequency of absorption is getting increased, shown right here. So from here, we can conclude that the energy of vibration is proportional to the frequency of absorption or the frequency of vibration. So if one increases, the other will increase. And this is inversely proportional to the reduced mass, mu. Let's brainstorm and check how much you have learned. Question 1. Write two factors which affects frequency of vibration. Question 2. Arrange carbon-oxygen bond, carbon-hydrogen bond, carbon single bond carbon, and carbon double bond carbon in increasing energy of vibration. Question 3. Out of the following options, which one will absorb IR radiations of lowest wave number? And the options are carbon-oxygen bond, carbon-fluorine bond, carbon-chlorine bond, carbon-bromine bond. I hope you will be able to solve these questions by yourself. And if you want any discussions or if you want to check your answers, just pop down in the comment box. I'll get back to you. Till then, keep watching